Okay, everybody. Welcome to MAPRG. Welcome to one of the last sessions of the IETF meeting 114 in Philadelphia. So you're nearly done, and this is an easy session, so sit back and relax. My name is Mia Kühlewind. Dave, do you want to introduce yourself?
Hi, folks. Good afternoon. I'm Dave Plonka. I'm remote at my home in Madison, Wisconsin.
Okay, so there's still a few people dripping in, but we will start as we have a packed agenda. So this is an IETF group, but this still falls under most of the Node well points. One point is intellectual property. Everything you contribute here is also contributing to the IETF, and you have to declare intellectual property. You might know this already by now, hopefully. Otherwise, please read it up. Then, as you can see, or as it's hard, not hard to miss, this meeting is recorded and will be published on YouTube at some point. So, which is also good. If you miss something, you can look it up. And also in the IETF, the privacy policy and the code of conduct apply. Usually, I think this group is like very friendly and we're very nice to each other, and we should generally do that. So you're very encouraged to ask questions, but always be friendly and be constructive and be positive. Again, this is an IETF session, so it's a little bit different than the IETF working session. In our case, we are mainly inviting researchers with really good papers and contribution, which might interest you, and provide you the presentations. In the slides, you find a couple of links that might be useful for you about what this group is about the agenda, about our mailing list. Please subscribe to the mailing list, even though there's not much going on. You will see some announcements which might be helpful. And then this one you should also kind of know by now, but I'm anyway telling you. If you want to say something at the queue, please join the queue in Meet Echo. Please also, if you don't want to contribute, please join Meet Echo, because that will also generate our blue sheets, and the blue sheets will tell us like how big our room is next time and these kind of things. So it's really important to sign up. When you're in the room, you don't need to put on your video and audio. You should actually take it off. But when you're in the room, you're obligated to wear a mask. And I think we are currently doing really well in this room. So thank you for that. For remote participants, we use the same queue. That's very convenient. And if you are not shy, we're happy to see you on video and have an interactive discussion with you. And that's it already from my start. As I said, we have a very packed agenda, so we will start immediately. The first talk is a heads-up talk, because it's a little bit kind of out of the focus of this group, what this group is usually doing. Our focus is on measurements of protocols. But we thought it might anyway be interested, so we invited Tal to give a short 10-minute heads-up of his work. And I think he's remote. Yeah,
Hi.
welcome.
Hope you can see me and hear me.
Yeah, we can.
Okay, great.
Do you want to request slide sharing so you can control them yourself?
Yes.
Miria, just since we didn't go through the whole agenda of the presentations today, I think we have 7, including this intro. And so people will have the 10 or 15 minutes, and then we have a few minutes in between. But I want to apologize in advance if we have to cut you off, but we're just going to try to keep to that so everyone has their allotted time.
Okay, Tal, the floor is yours.
Okay, thanks. So my name is Tal Mizrahi, and this is joint work with Jose Luz. We're both from the Technion. And actually, this is work in progress. But some of the preliminary results are already available publicly in archive. You can see the links at the bottom. Okay, so the conflict in Ukraine started in February, and we started looking at various measurement data from various sources. And we looked at publicly available data from all these different sources, and currently we're showing some of the results focusing on the first 2 months of the conflict. So one of the first things we saw was kind of an asymmetric trend around the border between Ukraine and Russia. So what we see here are speed test results, and basically download and upload speeds. And on the left side, we see Ukraine. We see the download and upload speeds as a function of time. And we see that starting from the beginning of the conflict, the performance degraded. And that's not very surprising, but on the right side, we see Russia. So starting from the beginning of the conflict, the performance actually improved. And it improved more significantly than in previous months. So that was kind of surprising. So a few words about the reason for that in a couple of minutes. Another thing we looked at was the Google search rate. Okay, so what we see here is the Google search rate, the rate of Google searches as a function of time. We see it in Ukraine on the left side, Russia on the right side. So in Ukraine, we see that from the beginning of the conflict, there was a clear degradation in the web search rate. And in Russia, there's kind of an increase in the web search rate. So if we consider what happened in Russia, it's slightly connected to something that was observed by the Cloudflare CEO, Matthew Prince, who said that they were seeing in Cloudflare, they were seeing a dramatic increase in requests from Russia to worldwide media, consuming world news, not just local news. And that's something that can be seen in the Google web searches and also in the Cloudflare data, the rate of traffic from Cloudflare to Russia. So that's one aspect of the performance in Russia. Another aspect is related to what happened at the beginning of March, which is the Russian government blocked Facebook and Twitter. And at the same day they blocked Facebook and Twitter, the rate of YouTube traffic also dropped. And so obviously we know that YouTube traffic, a lot of times you get the links from the social networks. So once the social networks are blocked, some of the YouTube consumption also drops. Also on the same week, Netflix announced that they were disconnecting their Russian users. And so what we see here is basically a significant decrease in the streaming traffic rate. And this can be a possible explanation of why we saw an increase in the performance in the speed test results. So we talked about Russia, but we haven't explained the degradation in the web searches in Ukraine and in general, the degradation in performance in Ukraine. And we believe that the main reason for that is the refugee crisis. So we've all seen these heartbreaking pictures, and we know that there was a very large refugee crisis. Millions of people crossed the border to the countries around Ukraine, and millions of other people had to be displaced inside Ukraine. And there are statistics that are published by the UN. We can see here a graph showing the number of refugees as a function of time. So if we take this graph and we take its first derivative, we see the rate of refugees as a function of time. So we take that graph of the rate of refugees, we see it on the left here, and we compare it to the rate of Google Maps traffic. Okay, this is what we see in the middle, the Google Maps traffic rate. And we see that there is a very clear correlation between these two graphs. And obviously, people had to move around, people had to travel to the border. So they had to use Google Maps. That's not surprising. What we see on the right side, the rightmost graph, is the mobile to desktop ratio. So again, people had to travel, people had to use their mobile phones. So we see a significant difference here in how the basically the usage profile changed over this period of time. One of the important things to point out is that in order to help the refugees, what the UN is trying to do is to try to map where refugees are staying. So the UN is kind of trying to keep track of how many refugees are staying in each country. And that's very important in order to help them. And in order to do that, what the UN does is it collects data from humanitarian organizations, from governments. And the data from governments is based mainly on border crossing. But the problem with that is that when people travel inside the EU, basically that's not monitored in any way. So if people cross the border, there's no way for the governments to know that. So the information published by the UN is not necessarily accurate regarding the EU countries. So what we're suggesting here, and that's what we see on the right side in pink, is to use publicly available measurements from the internet in order to try to estimate how many refugees are staying in each country. So in order to do that, what we did was look at Ukrainian websites. So for each of these Ukrainian websites, we looked at data that tells us how many visits or the visit rate from each country. So for example, we see here on the right side of the slide, we see google.com.ua, which is the Ukrainian version of Google. And we see that almost 5% of the visits to this site came from Germany. So more generally speaking, we took data on the top 15 Ukrainian sites, the most popular Ukrainian sites, and we used data about the visit rate from each country, and we computed a maximum likelihood estimation of how many Ukrainian people are staying in each country. And that's basically what we see in the graph here at the bottom, kind of a histogram showing how many people in each country. And basically, we believe that this methodology can be used in order to complement some of the data that is already published by the UN. So it can be kind of another piece to complete the picture. So that's in brief the work in progress that we're working on. Some more detailed results will be published soon. In the meantime, we would be happy for any feedback, and obviously we hope that the conflict will be resolved soon. So if there are any comments or questions, that would be
Thank you,
welcome.
Tal. We have one question.
Hi, Max Franke to you. So it's been pretty well known that Starlink was shipped, like a lot of Starlinks were shipped to Ukraine. Do you have any statistics on that, or do you want to try to incorporate some of that? Like,
Starlink was something that probably improved some of the connectivity in Ukraine, but we haven't analyzed any data about that. But that's a good point, yes.
And second question, you had statistics on the Google searches. Do you also have statistics on like the search trends? So what was searched? Do you see like a return to normal in what was searched for after a while, or is it still mostly conflict related?
Again, another interesting question, but we focused on the Google search traffic rate, and we didn't look into the actual content of the searches.
All right, thank you. Interesting presentation.
Thanks.
Hello, Ian Williams with Amazon. I just had a question. One of your slides had some points regarding the redirects from, or like visitors from certain countries on, like, say, Google Ukraine was, how many visitors from Germany. I know Google has like a no country redirect option. If you were in Google's shoes, would you have recommended, say, enabling that for this crisis to prevent this kind of disclosure, or do you think it wouldn't have been useful?
Yeah, that's an interesting question. It's kind of related to privacy, and actually google.com.ua was just one of the websites we looked at, and like you said, it may be affected by redirection. But when people look at news websites, for example, it's not really related to any redirections or something like that. So I think the fact that Google may be based on redirections is just one small aspect of this. I hope it didn't affect the results too much.
Gotcha. Cool. Thank you.
Thanks.
One more question.
Tianji, China Mobile. I remember during the war, and after a couple of weeks, the Starlink has installed it like a second pass. So have you ever measured anything for it, like a backup that's going to not damage, but it's going to at least relieve some burden from the damage the infrastructure through the Starlink? Thank you.
Okay, so if I understand the question, it was related to how damage and infrastructure damage affected the performance, and that's something.
No, the things like I remember after a couple of weeks, the Starlink has been installed over the sky on Ukraine, and then that is like a backup path. So have you ever measured anything? It's like a backup. Does that like relieve some burden from the measurement you have done for those damaged infrastructure? Thank you. On terrestrial network. Thank you.
Okay, so I think it's related to the first question, and we haven't gone into specific data that would allow us to analyze that aspect. So, but it's a good point.
Jack, the name is up here. Jake. The Q name is up here, so that's easy now. Okay, thank you, Tao. Thank you for this quick
Thank
update,
you.
very interesting. Next we have
Thanks.
Jeff. Do you want to share your slides over from? I do it, okay.
Good afternoon all. My name is Jeff Houston. I'm with APNIC and with my colleague Joao Damas, who is right in the back row. We've been doing a fair deal of work on various forms of measurement. And one of the more recent ones we started up, which was actually at the start of June, is to actually look at the incidence of the use of QUIC inside the context of HTTP3. Next slide. You know all this, don't you? Next slide. You know all that, don't you? Next slide. Standard intro, don't need it. The way we do this is trying to actually do extremely large scale measurements, equipping the server and using an online ad campaign to enroll almost unwitting clients. It's an ad. It's a really simple ad. If you click on it, I pay more. So if you see an ad from APNIC, just leave it alone, okay? Don't touch it. I pay more if you click. The ad system that we've configured does around 20 million eyeball-based networks, eyeball-based users per day. And one of the interesting things about ads is that the ad network tries extremely hard to enroll a different set of people every sort of period. So we don't go and inflict the same ad on the same set of users, and it actually gets around some forms of measurement bias. Because if you keep on touching the same endpoint, you just see that endpoint, you don't see a generic collection. So it's the best thing we've found to do a massive sampling of users. The downside is the script only does so much, and that's not much, because the only thing it's running is the injected HTML5 that you put through in the ad. And all it can really do is get a URL and do a delay. And oddly enough, that's enough, because what we do is equip the server. So if you make sure that every time an ad is impressed on a user, they go and do a collection of URLs, which is a DNS lookup followed by a web lookup, with a completely unique DNS name every time. So you're trying to get rid of, quite deliberately, most forms of proxying and most other forms of caching, which means all that material from the end client ends up hitting our servers. And we run a number of them in VMs all over the planet. This started as an initial measurement around IPv6 deployment. Simple stuff, 3 URLs, 1 dual stack, 1 v4 only, 1 v6 only. You're trying to see the number of folk who can get to the v6 only, interesting, and the number of folk who use v4 to get to a dual stack entry. In other words, the number of folk who are not, for some reason or another, doing happy eyeballs, and comparing it with the baseline of v4. So you can see how you do control and then experiment, bundle it up in an ad. We've done exactly the same thing for DNSSEC validation. And more recently, there's been an ongoing debate in v6 circles about how good are extension headers. Does fragmentation work? Does extension headers work, hop by hop or destination? And despite other claims to the contrary by other measurements, the ad system and the predominantly mobile devices that are eyeball networks in today's network go, no. But that's a different talk. What we're looking at here, though, is to actually see the level of penetration of QUIC in today's environment inside that eyeball-based network. Does QUIC actually happen? Next slide. Now, to do this, it's quite easy. We use Nginx as our server platform. It runs on a number of servers around the planet. 121.7 now has a beta version that actually does QUIC functions enabled. Yahoo, it all comes. We set up DNS basically in a wildcard configuration that does the HTTPS record, and we put in an ALPN value. Come back to that later. But certainly we're signaling that if you're looking for it, you'll find an answer. Yes, for this domain name, we support QUIC. Additionally, in the content header of this delivered 1x1 pixel, we put the alt service directive, which of course, if you're following what I just said, doesn't work. Because you get an ad, it fetches a bunch of URLs, the ad stops. It's a unique name. No one should ever ask for that name again. So when I put in a content directive saying, if you ever come and visit this property again, you will use QUIC, won't you? You're never going to come. So we had to actually alter the ad. And in this particular case, the ad scripts, go fetch this URL, start a 2-second timer, and then schedule the same fetch again. So tell the browser to go refetch to see how much we could tickle by just basically doing that refetch. That doesn't happen all the time. In that particular case, it happened around 1/5 of the time or so. The domain name in this case is constant. It's not unique for the second fetch because we're trying to trigger it. Next slide. So yeah, I just said that. Next slide. So there's a difference in QUIC whether the browser or whatever the user agent is triggering by the DNS, which will happen on the first time you fetch, or if it's using the content directive, which will only happen on the second time because the first is, nah, it's just TCP, TLS, it's HTTP2 or whatever. The second fetch makes a difference. So here are 2 lines for June and July. The red line is actually the second fetch. And what we're seeing is around 3.5% of users actually use QUIC the second time around. The lower down one is the blue line. And that's around 1% of users use HTTP3 on the first query. Next slide. Next slide. Now, you kind of think, particularly if you believe Apple, you're all running the current version of iOS. And even if you're running Chrome, the nagware is good enough now you're all running Chrome, what is it, 100, whatever it is. And it's actually quite difficult to go, no, I don't want to upgrade. No, 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 no. And you find yourself typing no all the time. So in theory, these vendors are doing a pretty good job of getting us all up to the same release levels, because the stuff that's out of date, you shouldn't be running anyway. So when we look at this by country population of quick use, next slide, what you actually find on the second fetch is a pronounced sort of bias. And the country at 26% or something, yeah, 28% is Malta. And even the Central African Republic in Africa, yay, a massive use of quick on the second fetch. I have no idea why, and I have no idea why those national variations. I just don't know. I don't think it's a measurement bias. It's the same measurement all the way around, but the relative level per country does vary a lot, which is odd. Next slide. And now we look at the first fetch. Now, don't forget, there's really only one browser that does this and one platform. Actually, I don't know if it's a platform. It's certainly Safari. I'm not even sure you can get Safari on Linux, but if you could, maybe it'll do the same thing. Who knows? But it's Safari on iOS, Safari on macOS. And oddly enough, maybe Denmark is just in love with Apple product. But certainly it has the highest rate of first fetch. And this is largely European, largely Northern European, as having the highest rates. And Africa, much, 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 much lower. So again, huge amounts of national variation. Next slide. So I actually had 4 questions when I looked at this. And I've sort of given you some hints already. Who's doing quick and why? What are the MSS values? You know, what's the connection failure rate like? Because putting all of our traffic over UDP port 443 is not something we used to do 10 years ago. And if you're using CPEs or firewalls, it's kind of, this is crap traffic, I'm going to drop it. So, you know, how much is being dropped? And last and not least, the whole rationale, or not the entire rationale, but a strong rationale for doing this, amongst others, was it's meant to be faster. Is it? So next slide. Let's try and answer each of those. Who's doing it? These are vertical columns, don't go sideways. Normally, the Android platform is seen in about 84% of ads. Ads see Android most of the time. Ads see macOS about 1%. Ads see iOS, iPhones about 5%. It's the market share of eyeballs as seen by Google's ad system. Fair enough. It's, as far as I can see with other stats, not too far off some kind of truth. When we look at the first fetch, almost all of the first fetches come from iOS and macOS. And certainly none from Android, you know, none from the others. So strong correlation, the platform is Apple's. When you look at the second fetch, the first fetches are still doing it the second time. The DNS is working, it's sticky. But now Android, the second time around, goes, yep, going to do it as well. So that's why the Android number rises on the second fetch. Next slide. So which user agent? Now, this is what the browser claims it's running. You know, there are lies, there are more lies, and there's the browser string lies, which are the best lies of all. So, you know, with a strong grain of salt about who's reporting what, you know, what you actually find again is Safari is first fetch and no others. So the 4.1% of Chrome, probably lying, who knows. On the second fetch, what you find is the Chrome numbers come in, 81% on Chrome, 16% on Safari. Firefox, which was only ever 0.8% of eyeballs, which is pretty low market share, and it's declining very, very quickly. First fetch, don't think it's doing anything. If it is doing DNS, it's not clear from this. And on the second fetch, again, 0.8% to 1% of share, not clear what's going on. Next slide. So who does it? Safari does it with the DNS HTTPS query. They may or may not also be sensitive to the content directive, but if they're doing the DNS query, that's the sticky bit. That's the bit that triggers it. The rest is going to happen anyway. But we also looked at the amount of HTTPS. 4 times the number of Safari clients asked than did. And you sort of scratch your head. and what little hair is left and go, hang on a second. If you knew enough to ask and the server goes, sure, why only 1 in 4 goes, yeah? You know, it's kind of, if you're going to ask, why not follow up the hint? We'll go into that. It's an interesting point. Secondly, the alt service. This is a low number. There's a lot of Chrome. And if all of Chrome says alt service, I'm going to do it, we're seeing a remarkably small capture rate. It is tiny. There's something going on there. So that's the first question. On to the next. Time is moving. Next slide. Yeah, right. The next question was packet size. In Quick, you must never fragment. So what's the distribution of packet sizes? The standard says in the first packet, pad to 1200, and around 45% do 1200. The maximum packet size I ever saw was a tiny percentage doing a little bit over 1350. So most of Quick sits in that magic thing, which is somewhere between 1200, the minimum, according to Quick, and a realistic maximum of 1400. No one's doing path MTU and extending beyond that. Next slide, next question. What's the connection loss? This amazes me that I'm only seeing half. Most of the problems we have with V6, and it's a much worse connection failure rate in V6, around 2.5%, is the packet being sent back. You give me a SYN, I give you a SYNAC, the filters and firewalls at the front of you go, V6 is evil, drop the packet. And so you actually see quite a visible drop rate. And you would have thought, or I would have, these CPEs sometimes were built in the Paleolithic era before dinosaurs, and you go, UDP 443, wow, that's evil. But interestingly, if I take one day and look at some 20 million sessions, there's the exact numbers there, the second packet comes through in all but 46,000 attempts, which is a phenomenally low failure rate of 0.24%. So whatever's going on, whatever reason the first packet hits me, and I've no idea if the first packet never got to me, because that's a problem on the other sort of direction in. I can't tell if I didn't get a packet. But when I got one, almost always the responder gets my packet and I get the next Quick packet coming in. So that handshake rate is better than V6. It is amazingly good. Next slide. Is it faster?
Jeff, just a heads up. You got about 3 more minutes, and that's going into your Q&A.
I am moving so quickly. Yeah, I know. Time is tight.
Thanks.
I use the browser timer. Browsers not only lie in the browser string, browsers lie in elapsed time. So taking the browser timer, I get this pattern. Next slide. There's a definite bias in the measurements to say the timed amount to fetch a Quick versus fetching over any other protocol, it's faster. A lot? No. But then again, there's a huge variation in RTTs. But on the whole, it's faster. For how many? Next slide. Around about 2/3 of the folk record a faster performance using Quick. That is significant. That is very significant. Does it work? Does it make it faster? Well, the browsers are reporting it does, on the whole, on average. Next slide. So those are the answers. I just told you that. Next slide. These numbers are low. Even Cloudflare with their radar reports far, far, far higher numbers, 30%. Next slide. Why? I should be seeing up to 90% in Chrome. Well, the issue is that 2-second timer, I'm too fast. If you've ever tried to do this manually on a Chrome browser, you actually have to hit the sentinel again and again and again to actually make it flick to Quick. So it's not deterministic and it takes time. So that 2-second fetch seems to be too fast. I have to wait longer for that directive to get sort of sticky inside Chrome for the next fetch to trigger. So I think I was jumping the gun. So that's bad. And that's why the numbers are low. Next slide. Right, why is the Safari query rate for HTTPS so much higher than the actual fetch rate? Again, what's going on is that I'm not giving hints. I'm only telling you use HTTP3. I'm not saying here's the v4 address and here's the v6 address in the HTTPS record. So Safari has to separately go and fetch that, and there's an internal race condition. Because if it gets an answer for the address records and doesn't get an answer for the HTTPS, guess what it's going to do? Speed is more important at that particular point. So we're now altering this measurement to actually put the hints into HTTPS to see if that will tickle the rest of the Apple side to actually go down the quick path from the start. I've been talking to Apple as well, and at this point it also seems that not every HTTPS answer converts to quick anyway. There's a certain amount of seeing how well it goes, and I think that reaping rate of query to fetch is actually being throttled somewhat by Apple itself. Secondly, why all the countries different? I have no idea. Are there regional defaults? Are the various pieces of browser software variant region by region? That's a browser question, it's not a Jeff question. Next slide. Wow, that was it. I think I'm in under the minutes there, Dave. There is a URL down at the bottom. I didn't do the QR code. This stuff is being run every single day with about 20 million users every single day being enrolled. As the picture changes, the picture on that web page will necessarily change to reflect current reality. And I'm done. Thank you.
Hello, Shivani Sahib, oops, Brave Browser. Thanks for this study. Just wondering, do you take into account ad blocking at all? And you know, like 35% of the web 5 years ago used an ad blocker.
Ad blocking is actually an odd activity. And this is the world as seen by ads. It's not the world. And there are certain providers, and there's a mobile provider in South Korea that does almost 100% ad blocking. I get very little visibility. Oddly enough, since March, as you saw from the previous talk, getting ads into certain parts of the world is now extremely difficult, and I see very few ads in those countries. Yes, but of the bits you see, it's all the same equipment. It's all the same view. And does ad blocking bias these numbers? I don't think it biases them per se. It's just the view as seen from the ad system.
Ben?
So I can't see the rest of the control slide, so you've got the cue.
Hi, Ben Schwartz. I had two notes here. One, are you killing the quick connection from the server side before the second fetch is initiated?
That's oddly enough an Nginx question. We
Okay.
did very little to the beta version of Nginx. So the
Right.
quick connection comes in. By the look of it, the 2-second delay happens at the instruct the browser, not 2 seconds between subsequent fetches, because browsers have more complexity than any operating system that ever got built. And so the variance in time between those two fetches seems to be an extraordinary amount of variance, Ben. And it actually is a separate piece of work to understand what the true variance is. Just as a quick add-on, the way we're going to change this is that we're going to change the ad to fetch the second time, wait 2 seconds a third time, wait 2 seconds a fourth time, and do this 7 times. If Chrome is going to flick over at some point in those 14 seconds, hopefully it's going to figure out that it can. If that's a kooky idea, I'd love some feedback.
Okay, so my feedback would be try something like HTTP connection close, the connection close header, or otherwise, like from the server side, close that HTTP2 connection as soon as you've sent the response. Because what you want is for the client to be initiating a new socket to see, should I use HTTP3? If the client already has an open HTTP2 socket to the server, it might just reuse it instead of going through the delay and complexity of opening up a new HTTP3 session. But if you can wipe all of your, if you can close all of your connections, then from scratch, it's more likely to start HTTP3.
Ben, that's extraordinarily helpful. Thank you very much. We will do that this afternoon.
The other thing I would say is for the HTTPS IP hints, in general, IP hints are only necessary if your target name is not dot. So we can talk about that in more detail, but I would encourage you to set your target name in the HTTPS record to dot, the magic default value, which means I'm not doing anything interesting in terms of redirection here. That makes the IP hint relevant.
Again, noted. Thank you very much. We will do that. Any others?
No, that's it. Thank you for
Thank
joining
you.
us. Usam? Yeah, just come up. You can request slide sharing. Do you want to do that? Yep. Now you should get it. Now you should select the slide. You still need to select the slides. Try it again. Now select them. There you go.
All right, so I'm Osama. I'm a PhD candidate at Brown University. Is it better?
Yeah.
All right. So yeah, everyone in the room knows that web performance is important, and better performance leads to better revenue and better user engagement. In order to do that, websites typically use CDNs, which have servers spread across the globe, typically called CDN edge. At the CDN edge, we have protocols like HTTP and TCP that controls the rules for request and response and rules for data transmission. Now an operator is required to select from among a different configurations option available. So for example, they may have multiple congestion controls and they need to select one of those. Similarly, initial congestion windows and a lot of other TCP and HTTP options. Now traditionally, the operator selects one set of configuration, then use homogeneously for the entire user base. The goal here is to maximize performance. But in this work, we asked this question that, is this approach really optimal? So if you're using a single set of configurations for possibly diverse users.
You have to go even closer to the mic.
Is
you
this
can also
one?
take it off if you want.
Okay, I'll try that. Is this one-size-fits-all approach really optimal? So in practice, users are not really homogeneous because they come from different regions. They have different last mile connections like 2G, 3G, 4G, and they have different devices. And the reason this makes it a challenge to select the right configuration is that protocol performance is sensitive to all these features. So assuming that we have different network path with different delay, different loss, and different bandwidth properties, the choice of optimal congestion control might be different. So a consequence of this observation is that the one-size-fits-all approach might not be optimal when we're talking about heterogeneous connections. So the goal of this work is to how to dynamically tune the networking stack so that we can maximize performance for diverse connections. But before I start talking about the system, let's go over some of the measurements that we did. So we started with a review of what are the three traditional approaches that are currently being used. The first one is default, where operators do not apply any explicit tuning, and they simply use the configuration that are set by default in either kernel or in servers. The second is handpicked, where operators run out multiple measurements in different regions, and based on that, they see that, okay, these configurations are working better, so we are going to select those. And the third one, we see some evidence in literature that people are building dynamic systems where they use algorithms like Bayesian optimization or reinforcement learning to tune their configuration, but they're mostly limited to either a single configuration like initial congestion window or a single layer like TCP. So in order to test that, we leveraged some public packet traces, and we got a network trace from a production CDN with billions of users across the world. And we used that traces to simulate a representative network condition in a local testbed. So what we did was for each of the network, we sweep the entire configuration space. So basically from the server side, we set every possible configuration for TCP and HTTP configurations, and we measured page load time for Alexa top 100 websites. So once this entire sweep was complete, we created an oracle that has like complete knowledge of the configuration network space and can always select the best configuration. So in this figure here, you see the improvement in page load time on the x-axis. And we see that for the handpicked configuration, there is some improvement, but it's mostly capped by 20% at tail, because handpicked configuration, though being manually selected, they're still static and they stay the same across diverse connections. For this orange line, for the TCP/CC, we used Oracle to tune a single configuration, which is congestion control. So basically, based on the type of network, we selected the congestion control that actually minimizes the page load time. So we see that at tail, the improvement, there's a better improvement, but around the medium is still the same. In the third case, the green line, we use Bayesian optimization, which is an algorithm for auto-tuning systems. And interestingly, the improvement results are not that good because we noticed that this algorithm is not really a good fit for network internet measurement case where we have lots of dynamicity, we have lots of noises, and it sort of derails the optimization process. And finally, we see the results for the Oracle, which tunes across the different layers. And we see, we make 3 observations here. First, at the tail, we see up to 70% and more improvement, which sort of motivates that dynamic tuning opens an opportunity here where we can optimize the page load times. Second, the gap between the orange and the red line basically motivates that we should use cross-layer tuning instead of tuning just a single configuration like congestion control. And finally, the gap between the red and the green line shows us that the existing algorithm for auto tuning are not that a good fit for this case. So we need a better algorithm. So basically, to achieve these goals, we built a system called Confignator, which optimizes the performance by systematically reconfiguring the networking stack. So Confignator takes into input features like website properties, a user's network or a connections network, and the device. And it tries to find a near optimal configuration in a minimal number of such steps so that web performance can be improved. So we faced a number of challenges in the design of Confignator. Since we are talking about internet measurements and CDN scale, there's a QoE associated here. If you test a bad configuration, then it's going to hurt performance and possibly revenue. And further, there's high dimensionality of devices and last mile connections. There's network dynamics because network changes over time, and there's noise. So these sort of properties makes it hard to create a performance model that can accurately represent the performance of a configuration so that we can select the right one. And finally, we have some system limitations that we don't have the networking stacks available right now that can tune the configurations in a low overhead manner. So we can use things like set socket OPT, but it means that we'll need to change application code itself, and we want it to be non-invasive. So basically, there's 2 sets of challenges. Some could be solved through algorithmic design, and others could be solved through system design. So in order to solve these challenges, we use a split plane architecture for Confignator. There's a central control plane called Config Manager, which runs in a data-driven manner. It sort of ingests data from all the servers in the edge, and it builds performance models through which it can know that which configuration should be used for a certain type of network. And then there's a data plane component called Config Agent, which is basically a piece of code that runs on every edge server. So for tuning the configurations, we wrote a kernel module and server callbacks through which we can tune TCP and HTTP configurations. And since this config agent is on the fast path, it caches configuration mappings that the control plane generates, and it used that for real-time configuration decisions. At the control plane side, the workflow looks something like this. So config agent that runs on servers sends data about a connection feature such as network and performance metrics like page load. And this information
So, and also that the percentage is non-zero. I'm kind of confused. Seems at some moment, like 20% of the time, you get worse. Yes, you get a worse result. What is the reason?
So we're talking about an online search algorithm case here. So definitely we're going to run into cases where while we are searching for new configuration, if we have no context about what a network, what works better for a network, we are going to definitely run into a case where we might be testing some configuration that have an adverse impact on the performance. But the property of the algorithm that we developed was that should be minimum. So the search should be directed. So that's why there is a negative impact here, but the algorithm tries to keep it to a minimum. So in the paper, we have experiments where we sort of try out different versions of the algorithm and show that this is sort of the minimum that we can get right now.
And we have Ben in the remote queue.
Hi, Ben Schwartz. Sorry, I missed a bunch of this presentation due to the glitch, but I wanted to ask if you've thought about the game theoretic questions here. How much of this gain is somebody else's loss? Is this a competition?
So that's a great question. So in the paper, we talk about fairness, but we haven't actively looked into the game theory aspect yet. So currently, we are working on some future work where we are trying to present this problem as you said, game theory between two players, and we are trying to see if we can find a good Nash equilibrium there. Because let's say in the future case, 10 or 15 years from now, if everyone is sort of running these sort of systems, then they're kind of competing against each other. Because if the choice of my competition changes, then my choice is also bound to change. So yeah, we don't really address the game theory aspect in this paper yet, but we are currently looking into it more in the future work.
Thank you. I would say that, I think that Nash equilibrium has a name. It's the IETF.
Yeah, so thanks for having you here.
Thank you.
Thanks. And next we have Marcus. You request sharing yourself, yeah? There you go.
Okay, hi, I'm Marcus. And together with my co-authors, we investigated how we can use TLS to fingerprint servers and find similarities among these server deployments to use it for further use cases. All right. I cannot.
It's not working. Try requesting again. I kick you out. Try requesting again. No, I didn't see it all. Okay. Then you just have to tell me when you go to the next
I'll do. Yes, so very short introduction to TLS. As you probably all know, everyone is using it. It's probably the de facto standard of all the encrypted communication on the internet. And it's also already quite old. So this means it has been grown to a very complex ecosystem. Which means now that in the initial handshake, the clients and servers, they need to exchange a lot of information about their own capabilities, such that you can find a mutual encryption base. And the idea of this work was now we can collect this metadata and we can use it to fingerprint a TLS stack on the server. Like TLS stack as a combination between config, implementation, and hardware. So next slide, please. All right, so if I'm talking about fingerprinting, what does it mean? It's basically just collecting characteristics about TLS that you somehow represent as a fingerprint. And then you build a database that maps these fingerprints to something that is just not directly related, but somehow useful. And for example, you could see these 3 fingerprints here, maybe one indicates an IETF web server, another fingerprint might indicate an Nginx Docker image, or even a malicious command and control server. Of course, these are all just indicators, but they work. So next slide, please. All right, so let's have a short look at the TLS 1.3 handshake and what information is there that we can use for fingerprinting. So as you can see, like the TLS works by that a client sends a server hello to a server that initiates the handshake. It contains the version, session-specific information, cipher suits, and a whole bunch of TLS extensions. Now the server looks at it and responds with the server hello that again contains a version, a cipher suite, and TLS extensions that are usually a response to the versions from the client. And then now TLS 1.3 specific, the handshake gets encrypted, you get these encrypted extensions, certificate extensions, and so on. And now all this information that is written in bold somehow depends on the TLS stack that is on the server. So if we collect this information, we can use it to fingerprint the server. Right, continue, please. All right, why should you need such a thing? So there were 3 applications we thought about how this could be used. First of all, an intrusion detection system could use such a fingerprinting mechanism to just gain an additional source of information. For example, it could fingerprint all the servers seen in network flows and then just look up the fingerprints in a database of known malicious fingerprints. Or it could use it in intel-wide measurements where you really use these fingerprints to actively hunt for new threats. Or you could use it to monitor your own servers, where now, basically, if the fingerprints change from your own server, something happened. This might be intended or unintended. You might untended change your software, or there has even been a malware infection happening that's somehow changing the TLS stack. Right, next slide, please. All right, so before I get into some results, let me share a small problem we had in the beginning. It was that we did this fingerprinting with some default client hellos from the library, and it just didn't work. So it was actually because we didn't collect enough information from the server due to this question-answer design of TLS that is intended to hide information. But as you can see, this is an example. So in the client hello, just looking at the cipher suits. In a client hello, the client sends a whole bunch of cipher suits. It could be hundreds of cipher suits to the server. The server looks at this list and selects a single cipher suit. From this example, you can see why TLS fingerprinting is already quite common for clients, because the client reveals a lot of information about itself. The server does not, so that's not a lot of information. And this led us came to the conclusion that, well, we should not use default client hellos. We need somehow unusual client hellos that really trigger new behaviors from the server. And we need to send multiple client hellos to the server that somehow complement each other so we learn even more. And like the third point was like, if we now send multiple client hellos and we want to have a scalable approach, we need to somehow find a trade-off between the amount of data we want to learn about the server and the costs of the whole fingerprinting. Like costs meaning the time it takes and also the impact we have on the server, because well, we probably do not want to perform an unintentional DOS attack if we take too many requests. All right, this led us to these 3 research questions. So first of all, how can we relate now similar deployments? How can we improve the effectiveness of our client hellos? And what's now the improvements of use cases? So let's have a look at the first research question. Basically, relate these servers by fingerprinting, but in a way that we extract all these handshake features from the TLS handshake in a way that similar deployments have the same fingerprint. And basically what we did was just extracted all this information, put it together in one big string. So this, you can see this is our format, but it's of course kind of arbitrary. You can see it contains the version, cipher, extensions, and also the TLS alerts, which are error codes from the TLS protocol. Because error handling is of course also implementation specific. And as we send multiple requests to a server, well, we just combined all these representations in one big fingerprint. All right, then let's have a look at the second research question. How can we improve now the effectiveness? Well, we did this. Basically, we had this challenge that we do not know every implementation. So how should we know what's the ideal combination of client hellos we should send? But what we can definitely do, we can somehow optimize the effectiveness of our client hellos. And we did this by doing this empirically, by basically just first of all measuring effectiveness, which is just a metric. We used the distinct number of fingerprints we were able to collect from the servers as metric. Then we performed a measurement with a whole bunch of randomly generated client hellos. And then we just picked a combination of client hellos that maximize this metric. And this way we generated 10 scanning client hellos we used in the following analysis. All right, so let's have a look at the last point. Does this work now? Therefore, we've designed a study with weekly measurements where we scanned these 2 top lists and 2 block lists over 30 weeks. We were able to collect around 100 million fingerprints, so quite a lot of amount of data we can test our approach on. And now the first use case we had a look at, so next slide please, were CDN servers, also content delivery network servers, because they were really great for us to test our approach on, because well, CDNs are basically a single actor deploying a large amount of TLS servers, which is exactly what we want to be able to detect. But they also provide us with a large amount of data. And
Sorry.
Okay. But their servers could also be verified through other means as well. So we can generate a ground truth through, for example, the AS or certificates they return. And that's what we did. We evaluated the CDN detection with this ground truth. And if you're not so familiar with classification metrics, so we used precision and recall. So precision is basically the number of correct classifications we did, and recall how many of these CDN servers from the ground truth we are now able to detect. So let's have a look at the results. So here can you see this precision and recall for the 4 CDNs we had a look at. So you can see the results for Akamai, Alibaba, Cloudflare, and Fastly. You can see that the metrics are quite high for all of them. So this detection works. Interesting, at least for us, was for Cloudflare and Fastly, it was astonishingly high. So the precision was above 99%, which means their TLS configurations are very unique among in the internet, and they're quite easily we were able to detect them quite easily. And what was also interesting for us, at least, was that with this method, we were able to detect also quite a lot of off-net CDN servers, sometimes in even unexpected places. So for example, for Cloudflare, we saw some servers, but they were actually reverse proxies a third party has set up that somehow proxied all the traffic we sent to Cloudflare. We don't know why they did this, but yeah, we saw this. All right, so and second use case we had a look at were command control servers. So where we now really are able to fingerprint or detect even potentially malicious servers. To make this more realistic, we just had a look at new additions to the tool list. And because this classification wasn't that obvious anymore, we now considered how often we saw a fingerprint from top list versus from block lists to kind of generate a score how certain we are. We now found a command and control server. And if this score was above a certain threshold, we just classified it as a CNC server. All right, so let's have a look at the results. You can see now the precision and recall again for this detection. Just on the x-axis now the threshold above which we classified the server as CNC server. And you can see 3 different sources of input data we used. So on the left, you see just the TLS fingerprints we've designed, which actually works quite fine already. So the precision is okay, let's say. The recall isn't that high, especially for the higher thresholds. We had a look at how to improve this, and we noticed some strange HTTP server headers, but they weren't really good enough to detect these servers. But if we combine both data sources, this detection now worked quite well. So in this case, we were now able to detect almost half of all the new additions to these block lists with the precision over 99%. This is quite good. And that's also how we expect people will use such a fingerprinting mechanism, just as in conjunction with additional indicators. All right, let me conclude our work. So in this paper, we proposed a selection of handshake features and then encoding as fingerprints as a mechanism to relate TLS servers. We also provide a methodology to find new client hellos for scanning, or just provide always some general purpose client hellos. We've made a study to really demonstrate the potential of this fingerprinting. And maybe you've heard of it. There's also this tool called YARM out there. It's also able to fingerprint TLS servers. It was announced around 1.5 years ago by Salesforce. However, we showed in the paper that our mechanism of fingerprinting is actually a bit more effective. And we've open sourced all our data and code if you want to try it yourself. Thank you. Sorry.
Thanks a lot. Thanks a lot for coming here basically for this presentation specifically, because you were very spontaneous, came here and joined us. I hope you had a good week.
Yeah, it was great.
We have Dave in the queue.
Marcus, that was really interesting. I wanted to ask you for a comment on, you had a slide up where you showed 4 CDNs and the varying precision and recall on them. Maybe I missed it, but how were you determining the ground truth about which CDN they were on? And the reason I'm asking is, what did you do with content that was multi-CDN? Like, did that come up? Did you see content that you wanted to validate, but that content provider is using multiple CDNs?
Yeah, we didn't investigate the multi-CDN case, but how we evaluated it was basically we send a request to the server, for example, for Cloudflare, if it could return us the certificate for Cloudflare.com, and if they were able, they definitely were a Cloudflare server.
Okay, any further questions? Then check out the chat as well. There were a little bit of discussion, and like also any further questions can go to the mailing list, of course. And we go to the next presentation. That's Konstantin, right?
Yes, I hope you can hear me.
We can hear you. Should be able to select your slides.
Well, somehow I'm not.
Okay. Then can you request it again?
Yes.
Let's try it again.
Now I can do it. Let
Okay.
me see where it is. Okay. I think you can see it now, right?
We can see you, we can see the slides, we can hear you, we're ready to go.
Okay. So thank you for inviting me. I'm Konstantin. I'm a PhD student at RWTH Aachen University in Germany. And I'm going to present you the results of our paper in which we took a look at the influence of resource prioritization on actual behavior of line blocking and the performance when using this with HTTP3. And this is joint work with Ike and Klaus. But before getting actually into the results, let me give you a short introduction. I guess most of you already know that, but just let me quickly repeat this. So we want to load a website, and for maximum performance, you would like to load, of course, all of the resources in parallel. So you would like to load the HTML, but you would also like to load already the resources that you discovered. So for example, the 2 images, the red and the blue one. And with HTTP1, you then just open multiple TCP connections to load these resources in parallel. However, this of course came with the overheads of opening multiple TCP connections. And because of that, with HTTP2, it was introduced to use just a single TCP connection where you then multiplex the different resources in streams and stream frames over this one TCP connection. However, the issue is that TCP is completely unaware of the streams, so it just sees an opaque byte stream, and this can lead to transport header line blocking. So let's say that, for example, for the blue image now, one of the segments, the TCP segments, is lost, which is just carrying the blue resource information, and basically we could use the other information for the red and the green resources, but TCP doesn't know this and just now waits for the retransmission of its lost segment. So we have to wait for one round trip time, and the browser does not get further information in that time. With HTTP3, instead, QUIC is used, and QUIC has multiple streams implemented on the transport layer, and these streams are now independent. So we don't have any interstream head-of-line blocking anymore. So, for example, we now have again the case where the blue resource information is lost during transmission. However, QUIC knows that this is only influencing the blue resource stream here, and the red and the green information can still be forwarded to the browser. However, for this to work, of course, multiple streams have to be active. And we can also get to the case where only one of the streams is active. And in this case, we get the same case that again, now this one stream is waiting for the retransmission. And because basically only this one stream is active, the whole connection is waiting for the retransmission. And how this data is now scheduled with QUIC, so which stream is actually sent and which stream frames is actually sent on the wire, basically depends on the server. So how the server decides how to send it and how the QUIC stack then decides. However, there's one thing, this is resource prioritization, which basically allows the browser to signal the server a preferred scheduling. So this can be used, for example, to say, hey, send me the HTML first. I need to discover all the other resources first, and then send me the images. And this allows the browser to have different prioritization strategies. And there are strategies used, for example, with Internet Explorer or the default for HTTP2, which was round robin. Then there's rated round robin. It has been used by Safari. Then there's an approach by Chrome, which uses a sequential scheduling, but they reorder that important resources are sent earlier than unimportant resources. And there's Firefox, which used with HTTP2 a mixture of rated round robin and sequential scheduling. And because this depends on because this influences how data is sent, this of course also influences the performance. There has been some related work on that. And basically this related work found out that for HTTP2 and also for HTTP3, the round robin and rated round robin approaches are actually worst, while the Chrome and the Firefox approach is actually the best or the better one. Why better? Because in that specific work, also website specific prioritization strategies have been discussed, and they found that if you have website-specific knowledge, for example, one image is very important, you get even better resource prioritization results in that regard. However, what we can also see here is that this sequential scheduling from Chrome showed best results here, although it would be worse for head-of-line blocking because we would then monopolize this connection, as we've seen in the example before. So basically, one would say, okay, this problem is now solved. We just know there is no influence. However, take this with a grain of salt because this related work, on the one hand, only looked at HTTP2, so no HTTP3, no head-of-line blocking free streams, and the other work looked at a QUIC stack at a time where QUIC was rather, or that stack was rather premature, and they disabled the congestion control and just sent at a constant rate and tried to avoid any loss. So loss hasn't really been looked at in the related work in this regard. And our idea was then to look at the impact of prioritization on the head of HTTP3 performance under loss. And for this, we then used different scenarios where we changed the loss burst size, the RTT, and the bandwidth, and then also tested different prioritization strategies. And we did this to identify the head-of-line blocking and the performance. And for this, we downloaded 35 websites. We replayed those websites in a test bed and then measured the speed index and the head-of-line blocking. So how many bytes were actually blocked during retransmission, and then tried this. And then measured basically the speed index. Let me just skip the test bed implementation in the interest of time. And let's get directly to the results. And for the results, what we will see is always the relative median difference to Chrome. And we use Chrome as our sequential baseline. And what we can see for the head-of-line blocking is that for very low bandwidths, we see an improvement in head-of-line blocking. So basically, the head-of-line blocking is reduced when we're using a parallel strategy in comparison to Chrome's sequential scheduling. But we can see that the differences are vanishing when we're using higher bandwidths. So we can see that this curve is always moving more to the right, up to the point where we even get a lot of overlap, for example, with the sequential baseline. And actually, those cases where we have this overlap, so in the CDF from 0.5 to 0.75 on the y-axis, that's actually points where the whole website fitted into slow start because the website was very small, and basically we could transmit everything of that without having any loss. So that's also one point that we have to look at. And for the speed index, we can see in comparable results where we see that for lower bandwidths, we can see even some improvements in speed index when using parallelism on the median case. So the curve is slightly moved to the left. However, these benefits are also vanishing with higher bandwidths. This is actually due to the same case. On the one hand, we have fewer loss, but on the other hand, we have a higher bandwidth. So more of our resources can be transmitted in that time. And we also have a higher congestion window with higher bandwidths. And that leads to the fact that sometimes the resources are just smaller than our congestion window. So even when we're using sequential scheduling, still multiple streams have been active because just the resources ended and the next stream could start. So this is the influence of the bandwidth on its own. However, this is of course introducing congestion loss. So let's also have a look at random loss. And for this, we looked at the 2 megabit per second case and then just added via NetM artificial loss from 0 to 5%. And what we can see is that again, for higher loss, so where more packets are lost, we can see that the head-of-line blocking is reduced, which is actually as expected. And this is due to the fact that loss is stopping many of the active streams for sequential scheduling, while for round robin, we have a lot of active streams and only a few of those are actually affected. And for the speed index, we can see a comparable effect. It's very subtle, so I added this black S-curve here, but we can see that there's a growing benefit for higher loss. However, this benefit is really subtle. So we can see that on the left side, a lot of the data points in the red circle are below our S-curve. And on the right side, we can see that a lot of the data points are above this. So it's not as strong as for the head-of-line blocking. And we were wondering why this is actually the case. So we then looked into the data a little closer and we found that different websites behave differently when using this. And because of this, we then looked into the correlation between loss and the speed index. And here we can see the correlation for the speed index and head-of-line blocking. And basically red means that there has been a correlation which was negative. So we could see that the head-of-line blocking has been reduced, but the speed index got worse. While blue means that we had a positive correlation. So the speed index was also improving when the head-of-line blocking was improving. And here we can see, for example, for wikipedia.org, that we can see only not very strong positive correlations or even red patches, so negative correlations, while for NewYorkTimes.com, we see very strong positive correlations. And the interesting difference between wikipedia.org and NewYorkTimes.com in our data set is basically that these are two different extrema for the website size. So wikipedia.org is our smallest website and NewYorkTimes.com is our biggest website. We can see that when we are looking on the left for the smaller websites, we can see a lot of red patches, while for the right side, for the bigger websites, we see a lot of blue patches, so very strong positive correlations. And we could see that the negative effects for the smaller websites were occurring because we could see that the head-of-line blocking has been reduced, but only slightly, because basically there hasn't been a lot of data on the wire in that case or in flight. And in that case, where we don't have a huge improvement in head-of-line blocking, we could see the negative effect of the parallel prioritization that also related work saw. While for the larger websites, we saw that the head-of-line blocking reduced more strongly, and then the negative effect was outweighed. I would also like to go into the details for other loss patterns and also what the impact of the round trip time is. However, I cannot go into detail here, but I can just tell you that the loss pattern is very important because when you have bursts, round robin is again really bad because you're then affecting a lot of the streams. And for the round trip time, you can tell you that higher RTTs increase the round trip time or the retransmission penalty. And so in smaller RTT cases, the effects are not as pronounced as we could see it here. Okay, so time to conclude. We saw that reduced head-of-line blocking via quick is possible. However, for that, multiple streams need to be active in parallel. And HTTP prioritization influences how many streams are active. And the easy way would be to say, just use round robin. However, related work said round robin is detrimental for performance. And we found that there's a new performance interplay between prioritization and the network. Round robin can improve head-of-line blocking and can thus also improve performance. However, mainly in cases for large websites, smaller bandwidths, higher RTT scenarios, or where random loss was seen. And we could also see that the new extensible prioritization scheme that has been, I think it has been a draft, I'm not sure if it's standardized now for HTTP3. It's this new scheme, we haven't seen a big difference between using the old scheme or this scheme here. So all in all, we can say HTTP3 prioritization is still website dependent, which related work found, but it's now also network dependent. Thank you.
Thanks for spending your Friday night with us. Let's see if we have any questions. Okay, but like you can check out the chat if there are any for questions. People can put them in the chat or contact you directly, read your paper, send emails. Thank you. We'll
Thanks.
move on. Nick, you're up next. Yeah, please unmute, Nick, and turn on your video if you like. And in the best case, you also request slide sharing, which is a second button at the top from the left next to the hand button. Okay, you are requesting screen sharing, but that's okay as well, I guess. But you also have to enable your audio. I don't think we can hear you yet. At the top, there's this kind of microphone sign you have to click as well. Because we can't hear you yet. You can also text me in the chat window if that doesn't work for you, and then we come back later to you.
Let's do that, Miria. I also wrote to Nick asking him if his pre-flight test worked, but I'd suggest he rejoin and do the pre-flight test to show that your mic's working, and then we should be able to good go in minutes.
Yeah, please rejoin or maybe try a different browser. Okay, we go to the next presentation. That's Fong. Are you around, Fong? Perfect.
Hear me? Oh, okay.
So the next two presentations are both about DNS encryption, so they should fit very well together. Great to have you here, Fong. Yeah, okay, we try the other slides. That's probably easier. Now you should be able to select your slides.
Sure.
Okay, perfect.
Okay, so I hope everyone can see my slide. Just give me 1 second.
Okay, Nick, we can see your video now, but we're taking Fong's presentation
Oh.
first, so we have to wait a little bit longer.
Oh, okay. Sure, no problem.
Yeah,
then.
no, but we can hear you and see you. That's great. So we take Fong first anyway, because you're all set. We can see you, we can hear you, we have your slides, so you can go ahead.
I mean, okay. So just let me figure it out. I have a little bit of problem here. So, okay, hello everyone. My name is Fong, and I'm a postdoc researcher at the University of Chicago. And today I will be presenting our work on measuring the accessibility of domain name encryptions and its impact on internet censorship. And so, regardless of the expansions of HTTPS traffic, plaintext domain names are the last piece of unencrypted information that is still largely visible onto the internet. So where is domain name information exposed? And the slide here shows you the common places where domain name information can be monitored by any network level observer. For example, your internet service provider or your network administrator. So these are the network packets that I capture when visiting example.com. And the first place that you see here is through the DNS query and response. And after getting back the IP address of example.com, the client initiated the TLS handshake to port 443. And the second place here you can see is in the server name indications, where you can see sample.com domain name. And the exposures of the domain name informations in these two channels have led to many security and privacy problems, and make most network connections susceptible to domain name-based internet filtering. And so domain name, to address those problems, many domain name encryption technologies have been introduced in recent years, including DNS over TOS, DNS over HTTPS, and encrypted SNI. Some of you know here that they being reported to encrypted client hello, but still being developed as an internet draft. And so in the new setting, the users and the DNS resolver first establish an encrypted channel, which could be over HTTPS or TOS. And after that, DNS query and responses are sent over this channel. And during the TOS handshakes, unlike in previous TOS versions, since version 1.3, the server name indications extension can also be encrypted. And this new proposal to prevent any on-path observer from seeing the plaintext domain name information. And so, it is clear that domain name encryptions can help improving the security and privacy for internet users, but it's also take away the visibility into plaintext domain name from the network traffic. And so that has motivated us to investigate how domain name encryptions impact internet censorship. More specifically, we want to know whether any censor out there are taking a step ahead to block domain name encryption technologies. And if domain name encryption is not blocked, which means it's accessible, then can it help to circumvent traditional internet censorship technology like DNS poisoning? And so to that end, we measure the accessibility of domain name encryptions by building this system called DNI based on a network of distributed VPN vantage points recruited by the VPN Gate project. Give us the capability to conduct measurements in 85 countries around the world. And what we do here is we take the input from many other censorship measurement platforms, including UNI, ICLab, and Censorship, to see what domain that this platform has been discovered to be censored. And then, and also we input 71 DOT and DOH resolver to this infrastructure to conduct measurements. What we do is we first do DNS measurement by sending out DNS queries for these domain names to see if any of them get blocked or not. And then later on, we do DNS resolutions over TOS and HTTPS to see if we can properly get back the answers that we were anticipated. And finally, while doing all of this, we capture the network packet to later on analyze and see how, in which way that sensors out there are blocking these new technologies. So here is what we found. From the measurement conducted by this system, we could conclude that censorship based on plaintext domain names is still widespread. And as DNS tampering has been detected in many countries, so here the top 5 countries, which is China, Russia, Iran, Indonesia, and India. But we didn't observe any DNS-based blocking of the domain name of major DOT or DOS resolver, like we have DNS.Google, or we have DNS-Cloudflare.com. Those are popular DOT, DOS resolver, but we didn't see any tampering, DNS tampering when resolving those. Only one case in China that we found that the Great Firewalls tampered with the resolutions of this domain name, which belong to Hurricane Electric. And so we then conducted the accessibility test for 71 DOT and DOH servers by sending encrypted DNS queries to them from all of the vantage points that we have. And to better highlight the findings, we compute the data of the top 5, not 3 countries. When I say top 5, not 3, this classification is not done by myself. The top 5, not 3 countries classified by the Freedom House. and that they have the largest number of failed resolutions, and namely China, Russia, Iran, Saudi Arabia, and Venezuela. And it's visible on this plot that from March 2021, there's a decrease driven mostly by the blocking effort of China against DOT and US resolution. And so here I go more into detail to show you how they actually go and block it. So this is the packet capture when I was trying to do a resolution using DNS over TOS. What you're seeing here is, because this DNS over TOS is standardized with port 853, and this port is not used by any other popular applications. And so blocking the IP and port 853 is trivial and sufficient enough to hinder the use of DNS over TOS. And that's how China is blocking it. And so this slide shows us how they block DOH. What you're seeing here is I try to use DOH service of Google Resolver. And what have finished here is that I could finish the DNS lookup for the IP address of dns.google.com, right? But then as soon as I start the TCP stream to do the DNS over TOS, over HTTPS, then it's blocked. So the thing here is the IP address of popular DOS resolver are widely known, and therefore dropping traffic based on just the resolver IP and port 443 pairs is enough to block DNS over HTTPS too. Although, you know, among our community, we say if we do DNS over HTTPS because it's run on port 443, then it's just more collateral damage. But just think of like what else, like what other service that may run on 8.8.8.8, right? So it's just obvious. And so another blocking that we observed was in Saudi Arabia, which is against Cloudflare resolver. And we observed this to be a centralized effort because we observed the same blocking signatures in multiple ASs in this country. So whatever the domain name and with cloudflare-dns.com, as soon as we start the TOS handshake, we complete it, we send a client hello, they detect it in the client hello, then there's they inject the reset packet to tear out the connection. And so for the case of Russia, we see a decentralized blocking efforts against encrypted SNI, which means that we don't see it everywhere in Russia. There and here in the countries that we see some efforts of blocking this protocol based on the 2-byte signatures of encrypted SNI. Basically, this blocking mechanisms is similar with the way Great Firewall of China has been blocking it since, I guess, October or September of 2020. And so with that, we move on to answer the final questions that we ask is like, if all of these technologies is accessible, it's not blocked, or somehow we get it to work, then can it help to circumvent traditional censorship mechanisms? And so we use encrypted DNS when crawling censor website. And so this encrypted DNS in some country, I say, oh, China block it, Russia block it, Iran block it. So the way we do is like we have our own DNS over HTTPS server running on a non-standard port, and we find that none of the country that block it. So they don't do any like fingerprinting on the traffic. They just use the IP and port to block it. So the takeaway here is that if we run out of DNS over HTTPS server, we don't get blocked. And we use that to visit the website that were found censored earlier. And so the finding is that a lot of them in countries like Russia, Indonesia, and India, you can actually defeat censorship just by using this technology. But then in China and Iran, we couldn't do it successfully because a lot of this website, they don't support encrypted SNI. And so you could bypass DNS censorship, but then at the TOS handshake, you still expose the domain name information. And because China and Iran, they also have filtering at that layer. So we couldn't bypass it. And so the key main takeaway from this study is that domain name encryptions can help to partially circumvent internet censorship based on plaintext domain name, based on plaintext DNS resolutions. However, notorious censors has taken a step ahead, to prevent the deployment of domain name encryptions by blocking DOT, BOS servers, as well as encrypted SNI connections. And to address this problem, new domain name encryption protocols should be designed and deployed in a way that blocking their traffic is not an option without causing huge amounts of collateral damage. And SNI-based blocking is still possible, as encrypted SNI has not been widely adopted. And when I say an encrypted SNI, now it should be encrypted client hello. And to tackle this problem, we should really deploy these technologies at a larger scale, and hopefully universally to discourage a censor from blanket blocking. And with that, I'm happy to take any questions that you may have.
Thanks a lot. Interesting results. Very good for this audience. Let's see if there are any questions. We have some time. Dave.
Yeah, thanks, Vong. This is interesting. Just following on to some comments in the thread was, I think a reasonable follow-up question would be, do you know of any work that tries to classify the types of censorship, for instance, so that you would know if the censorship was trying to block malware or sexually explicit content as opposed to, say, a political motivation?
So in the case that we found here is most of the domain that we found to be blocked, actually a lot of them are political motivated blocking rather than malware, because this study is based on the block list that used by the Citizen Lab, which is mostly politically motivated blocked website.
For somewhere to send people if they were interested in classification there. So that block list, and maybe does UNI have anything that is about classifying the censorship types?
It's not in this study, but if you're interested in classifications, I have a work on just the Great Firewall of China, where I break down that they blocked 300,000 websites, and what are the portions of that belong to business, belong to pornography, belong to malware or malicious website. I'm gonna put the name of that. It's called gfwest.org. That is the website that you can go and see the breakdown of websites being blocked specifically in China.
Thanks so much.
Thanks, Patrick.
Hello, thank you for this. Pat McManus, I'm with Fastly at the moment. I really like your takeaways, thank you. One sort of nuance I want to point out is that you're focused mostly on the censorship case. And even in these cases where there's blocking and censorship is indeed applied, you still preserve the property of confidentiality of what people are looking up, rather than having to say what your destination was going to be. With an encrypted DNS, you just can't ask that question, right? What's being blocked is your connection to a well-known resolver. And that is a strictly better situation than you were in before of someone looking at the plain text and throwing that away. So even in these situations, we have ratcheted the problem forward, at least from a confidentiality point of view. I guess my second note is you are making sort of a call here to back encrypted client hello. And I just want to say I'm actually bullish on that. I think that's going to work out. The distinction you draw here of the old ESNI and the migration to encrypted client hello, I think all you're seeing there are those gears turning a little slowly, but I don't think it's really a rejection in the marketplace. So cool, thank you for this.
Thank you for the comments, and I totally agree on that. So these protocols are I think they are, of course, they're not gonna go be employed and address all of the problems out there. Of course, they will introduce new problems that we may face too, into how we're gonna do the packet inspection, how we're gonna do malware detections and all of that. But I believe these technologies are very important for our online privacy. And in the long run, just like I believe like 10 years or even 15 years ago, when people are talking about moving from HTTP to 100% HTTPS, a lot of people was very like susceptible about that. But then now you see like more than 90% of the web is like over HTTPS. And just similar to that, I believe there will be a day that encrypted client hello will be deployed universally, and hopefully it will help to address some of the problem about surveillance censorship.
Thank you. Yeah, then we finally go on to Nick. You can try to join us again.
How about now?
Yes, we can hear you. We can see you.
All right, we're getting somewhere.
So
Let's see,
actually,
I
it's
really
easier
wanna share my
if you don't
screen.
do screen share, but only slide share, because we uploaded your slides. So if you
Oh, okay.
yeah, we can wait. We can
I
stop
think
that.
it's
And
gonna
if you,
work.
we can trust
Oh my
press
gosh.
the paper sign right next to screen share.
Okay. Yeah, it's open system preferences. Okay.
No,
What?
yeah, stop that process. Just hit the paper sign.
Oh, here. Okay.
Between the hand and the screen share sign.
Hang on a sec. All right.
Or I can
Oh,
also.
it wants to quit Firefox and reopen this.
No, wait, I do it. Stay
Hang on.
there.
Okay. Later. Okay.
No, this is.
Yeah, let's use your slides. I've got slides here, but let's just do it your way.
No, I selected the wrong slide.
There's this great software called Zoom that actually works. Let's see.
Fantastically well, Nick.
I can see myself behind you in the room. That's kind of cool. I don't know if we're gonna get slides. I could go back to Brave. I could try that again, but
No, give me 1 second. Sorry, this is my fault.
okay.
Because they should be here.
We'll
but
get
they're
there. I'll
not.
just talk fast. This is. Let me just see if I can.
Yeah, Dave, did you upload them already, or did you convert them already? You can also do that. Okay.
Your screen, yeah.
There
I
are
do
so
wanna
many
share.
solutions here.
Yeah, so there it is. Yikes. Oh man, okay. Hey, look at that. Amazing. Okay. Hi, everyone. Great. I'm going to talk a little bit, and thanks to Miria and Dave for the invite to the group. It's great to see a lot of familiar and friendly faces. I'm going to talk about some work we've been doing to measure the availability and response times of some of the public encrypted DNS resolvers. I think as this group probably knows very well, I'm not going to spend any time on the background of encrypted DNS or DNS over HTTPS. As this group probably also knows pretty well, there are some so-called mainstream resolvers. I'll define what I mean by that in just a minute. But what we were interested in sort of looking at in this work is if you go to like DNS crypt proxy, there's a whole bunch of other DNS DOE resolvers, et cetera, that are listed on that page as you can use these. And so we wondered about that. We wondered, well, can you actually use them? And if you go to that link there, and there's a draft paper linked off of that page. It's fresh. You can see the full list. I'll put some examples up in just a minute. But the gist of this work is to try to really figure out how many public encrypted DNS resolvers are out there that you can actually use that aren't some of the usual suspects. And credit to Rania Sharma, who did a lot of this measurement work. Rania is actually did this work as a high school student, and she will be an undergrad, a first-year undergrad at University of Chicago in the fall. So hopefully we'll have a encrypted DNS expert 4 years from now who's ready to go out into the world. Part of this you can see, I think, from the page is there's an open source tool for measuring encrypted DNS performance that we used to perform these measurements. You can find it from that page I linked. That's in ongoing and active development, actually, as we continue work in this space. DIG, et cetera, have added DO and DOT support, and so we're going to be redoing a bunch of these measurements with DIG. But some of what we've released includes not only DO lookup time measurements, but also web response time measurements. So using the tool that we developed, we've measured those response times using a very large list of resolvers, including the mainstream resolvers, which I'll show some comparisons of, as well as what we call non-mainstream resolvers. And then we study how the performance of these resolvers differ based on vantage point, because you can imagine some of the usual suspects, they're highly replicated. But some of the others that are further down on the list, they may be deployed in a particular country or continent. And so if you're going to measure that performance, you probably want to measure it from the nearby as well as not nearby. So we did our measurements from a vantage point in North America, Europe, and Asia. We continue to expand on this work. I'll talk about that in the conclusion, because we only did it from these 3 vantage points, and it was a one-time shot, but we're extending that. First, let me sort of talk about the context. So modern browsers provide a few choices for encrypted DNS resolvers. We define those as mainstream, so you can see the choices here. This, by the way, is as of a couple months ago. It's constantly changing. So if you see a mistake, please let me know. The performance of these is of course of interest, and the draft paper that I linked does provide measurements on all of those, and we do comparisons against those. We were also interested in like all these other DO resolvers that are supposedly running. Are they actually running, and can you use them, and so forth. So we measured a bunch of different things. One was availability, which DO resolvers are active and responding to queries. We also wanted to measure the round trip latency to each resolver, I should say, because we want to measure our lookup times against, I guess, in the context of what that round trip latency is. And then finally, of course, what's the query response time? The experiment setup, we had 3 global vantage points, as I mentioned. Here they are. This particular study, we did queries to Google and Netflix. And this is not a full list of the resolvers that we queried for that. I couldn't fit them all on the slide, but for that, you can look at the paper. But there are, I think, 80 or 100 some odd resolvers that we did query. So you can see some. This is just the top of the list. So you can see some usual suspects in here, and you can see some perhaps less familiar faces. First thing we looked at was, are these non-mainstream resolvers available? And turns out that a lot of them, we saw a fairly high failure rate, as you can see here. In a lot of cases, we were not able to even connect to the resolver. In some cases, we were able to connect, but we got like an HTTP error code status. In other cases, we had SSL, TLS errors or other errors in HTTP. So you can see basically about a 78% success rate, which is well, let's leave it at that. Good. Okay, so here here what we do, and I hope this is large enough for you to see, but here what we do is we look at how the mainstream resolvers perform, and I'm going to walk through this kind of one box plot by one box plot. So these are box and whisker plots, if you're familiar with those. We're looking at distributions, and you can see going down the list here, we've got resolvers. Okay, these are sorted by median DNS response time. Yep, sorted by median DNS response time. Oops, and this is DOE. Okay, for each resolver, you can see the red or the top of the group. It's a grouped box and whisker. You can see the ping time. So that's just like ICMP ping, and again, that's a distribution. So you can see a green line for each of those that shows like what's the median ping time, and you can see some of these are pretty close, right? If you're in North America, as you sort of move, as you sort of get to less replicated services or resolvers, you can see some of them moving a little bit further away. Bolded are what we define as mainstream resolvers. Those are the ones that I showed on the previous slide, and those are offered as options in your browser. And so things to pay attention to here are the bolded ones and then we basically got 3 of these, 1 per vantage point. So if you want to just kind of focus on the main takeaways, you could sort of start by looking at North America. And this is, by the way, this is from, I'm showing one of these. The paper it does this 3 different times. So you see North America local. We're measuring this group here are North American DOE resolvers as measured from North America. And we put the mainstream DOE resolvers on all 3 because we assume they're replicated in all 3 places. But like Draco Plan9ns2.com, that's sitting somewhere in North America, whereas public DNS IIJA.jp, that's in Japan. So that's why you see that on the Asia plot. So A is North America to North America, local. B is North America to Asia, so that's why you see higher ping response times here. You can see these are clearly geo-replicated. And then here we've got North America to Europe. Okay, so bunch of things you can take away here. And then, as I mentioned, just to repeat, these are sorted by median DNS, encrypted DNS response time. So the better performing ones, according to that median, are towards the top. So as expected, you would see this mainstream resolver is sort of closer to the top. There are some surprises, I think, like, for example, ORDNS that HE did. So Hurricane Electric apparently runs a pretty decent encrypted DNS resolver that is replicated and also performs pretty well, even though it's not a browser option. And then some of these others, they may be reasonable options depending on where you happen to be sitting in the world. One of the things that we didn't do in this study, I notice I'm coming up on time, that we are in the process of doing is also doing the page load times. This is just DOE response time if you presumably also care about web page loads. But I think this is pretty interesting for a number of reasons. I think we expect the mainstream resolvers to perform pretty well. But another thing that I think the IETF is considering a lot is consolidation, right? And for the healthy, for a healthy DOE ecosystem, it is good to have many organizations that operate DOE resolvers that we can use that perform well. And I think there's good news and there's news here. I don't know if I don't know if there's bad news, but there's certainly information here about other resolvers that others can use and other places to invest. This is, I think, my final plot, and then I'll kind of come to conclusions. But that was a little that was a little bit of an eye chart. And so one of the things that we've also been sort of looking at is, how do these resolvers perform with respect to network round trip time, right? Because that's the fair comparison in some sense. From like wherever we happen to be sitting, where is that resolver, right? And then you would expect it, like hopefully, you know, at least on your initial lookup, you've got a couple round trip times to set up your TCP connection and your TLS connection. But then hopefully you're not adding too much latency on top of that. And you can kind of see how that is if you look in sort of how's it going in North America, Asia, and Europe. And you can, in each point here, each blue point is a DOE resolver. And so I don't know what's good. Things should not be probably below the line. So there's, but you can see here that, you know, how we're doing as far as, you know, the existence of performant DOE resolvers around the world. So this is all in the paper that's linked. There's slides are also linked from that page. So in conclusion, you know, I think the non-mainstream resolvers have a higher median response time than the mainstream ones. Typically speaking, the mainstream ones appear to be replicated. However, a local non-mainstream resolver, you know, sometimes actually exhibits equivalent performance as compared to some of the mainstream ones. Hurricane Electric in North America and in general, all DNS in Europe, and there's one in Greece also that actually seemed to perform pretty well, even though it wasn't globally replicated. So I think this presents some interesting early findings, some opportunities. As I mentioned, there's a bunch of ways that we're following up on these measurements, and I look forward to the feedback of the MAPRG. And again, thank you so much to Dave and Mirya for the invite and the privilege of speaking to the group. Really welcome the feedback. Thank you.
Thanks, Nick. We don't really have time for questions anymore, but
Yeah,
this was really
no
interesting
worries.
for sharing this. And I also don't see anybody in the queue, but you know how to reach Nick. There's this chat, there's mailing list, there is private email. So
Here's a website that has a link to the slides, the paper, and you can reach me from there too.
Cool. Nick, I posted that link in the chat too for people.
Sweet.
Yeah.
Thanks
Okay,
much.
that means we're at the end of the session. We're at the end of the IETF meeting. I just want to say one more thing. This time we only got a very few contributions, and we were very lucky that we reached out to some people and they said spontaneously yes to present here, and so we had a nice program. But we're depending on contributions, so like let people know about this group. If anybody's doing measurements, please come to us and tell us about it. That's very helpful. Dave?
Those of you who are traveling, happy travels home, and we will see you in the fall, if not before.
Thank you. Bye.
Bye-bye.
Ich nehme mit gleich ein Taxi, aber wir haben jetzt noch ein Meeting. Also wir werden wahrscheinlich last minute auftauchen.